Okay, hello. We're here to talk about our third method of solving systems of equations. All right, the first method was by row reduction in algebra. Second method, which we have discussed, and we have a problem set due on those methods, I believe. Second method was to use matrices, which really is row reduction in disguise without the variables listed. And the third method is something called Cramer's rule. And we're going to do a couple videos on Cramer's rule. It gets to be involved. And let's not forget that in the last video or an earlier video, I had showed you how to use the calculator to do some of the work in determinants. And Cramer's rule uses that. Okay, so what we're going to do, I'm going to go through Cramer's rule and I'm going to illustrate it with several numeric examples, and then we will see how we proceed from that point. This is going to take a lot of organizational skills because one slip up in the computation and everything is going to go south. Okay, so what we want to do is we want to be a little careful with our computation. Okay, so let's begin here. And these notes are in the chapter 12 section, along with the notes on matrices and determinants. Cramer's rule uses determinants to solve systems of n by n linear equations. So we're talking about square systems, basically. Okay, first one that we're going to look at is a 2 by 2 linear system. And of course, needs to be in standard form, which in English means the x's are lined up, the y's are lined up, the constants are lined up, and the equal signs are lined up. Okay? Here's what the solution is. And it's a mess. Okay? X equals b1 times c1 minus b1 times c2 over, and y equals, okay, you get this from algebra. So let's take a few moments and let's go through why that is. I'm not going to go through for the 3 by 3 case, and of course you don't really need to, but there are certain patterns here that lend themselves very well to work with determinants. So the first question is why Cramer's rule works. Okay, now this is not something you have to memorize. I'm just pointing out to you that this method is not a method that somebody dreamed up and is a mystery. It's actually comes from solving the general case. So let's solve this 2 by 2 linear system. If we're going to use algebra, well, we first have to decide, do I want to eliminate the x terms or the y terms? So I want to go from a 2 by 2 system, 2 equations, 2 unknowns, to a 1 by 1 system, which means 1 equation, 1 unknown, and then I do that backtracking. Okay, so let's solve algebraically for x, and our idea is to eliminate the y. Now, the way we eliminate the y is we get the coefficients in front of the y to be the same. So what I'm going to do is, if these were numbers, b1 and b2, I'd multiply them, I'd get or something I could use as an LCD. So what I'm going to do, I'm going to take equation 1 and multiply it by b2, so it'll have the b2 that appears here. I'm going to take equation 2 and multiply it by b1 to match the b1 here. So look at what I get. First equation times b2 is this, and second equation times b1 is this. Now you're going to notice that the coefficients in front of the y term are the same, so it's subtraction that will do the deed for getting the y's to cancel. And then we'll have gone from a 2 by 2 system to a 1 by 1. So if we do subtraction, you get the top term minus the bottom term here. The top term minus the bottom here cancels, and then you get b2c1 minus b1c2. And the idea, if I want to solve for x, I factor out the x, and I divide by this a1 b2 minus a2 b1, and here's what I get. Okay? Now, what we're going to do is we're going to assume that this is right, which it is, of course, and we're going to go back here, and we're going to see what that has to do with determinants. Now, here's what Cramer I don't know much about him historically. He may not have even been the first man to have noticed this, but he's the one who gets credit for it. All right, here's what he noticed. He noticed if you look at the denominators, first of all, they're the same. Okay, and if you look at the A1, B1, A2, and B2, you will notice that A1 B2 minus B1 A2 is simply the determinant of the coefficients. We symbolize that by D, D for determinant. Okay? Um, so, again, you look at the coefficients, and determinant D would be A1, B1, and then the second row would be A2, B2. And if you go through and you use the rule that we've learned earlier to evaluate that determinant, this is what you get. Okay? And it works out to A1, B2 minus A2, B1. So he noticed that. Now, what he also noticed, which is kind of cool, is that, well, we have a little bit change in notation here. So capital D is going to stand for the determinant of the coefficients of the x's and y's, and D sub x is going to stand for the determinant with the x coefficients replaced by these constants, C1 and C2. So if you replace them, you get C1 and C2 and a B1 and B2 here. So this is the determinant, which is symbolized by D sub x. Similarly, the determinant sub y is when the coefficients of the y are replaced by the constants here. And then you can see, if you go through the process of computing this, the top would be C1 B2 minus B1 C2, exactly what we get here for x. And if we go back and substitute in that why it works routine, we would find that the top on the y would be what we get from determinant y. So this is what Cramer's rule says in English. X is the quotient of the value of these two determinants. Y is the quotient of the value of those two determinants. And very easy to apply, but you got to be a little bit careful. Okay? So let's look at an example, and just keep in mind, whenever we're working with division, you can't have a zero in a denominator. We'll talk about things that go wrong later on, but right now we're just going to suffice it to say no unique solution if determinant D, which is the determinant of the coefficients in the denominator, is 0. Okay, so let's just make sure, and then we'll go to 3 by 3 case. Okay, so right now let's look at an example. And there is on Blackboard, I made up for you a combined homework and classwork worksheet with the answers here. And the solutions are on Blackboard as well. I'm going to be working from the solutions now. But if you want to test your skills with this, these are what you should look at. Okay, these are not something I'm collecting. These are just things that you should look at in order to see if you understand the topic. And what I'm going to do is I'm going to take the examples I'm going to do shortly right from these. Okay, so everything that I'm doing, you will be able to see on Blackboard. Okay, so let's look at the first one. First example is the system of equations negative 4x plus 3y is negative 11 and 5x plus 4y equals 6. And this, of course, is a 2 by 2, and we're going to solve this by Cramer's rule. Now, the idea is, of course, that we have options. You know, we could do this by algebra, you know, try and eliminate the y. We could do this by using matrices, but the instructions here are to use determinants and Cramer's rule. Okay, so here we go. We start out x equals d sub x over d. So let's find what these are, and then we'll work them out. D, and of course these have to be lined up in a proper way with the equal signs lined up, the x terms, the y terms, and the constants. Okay, so let's get D. Negative 4, 3, 5, 4. Okay, and they would be the same in both denominators because both of these have a D. Okay, all right, now to get D sub x, we replace the coefficients of the x terms by the coefficients of the constants. So you get negative 11.3 and 6.4. And we work these out and we do their quotient, and that would be the value of x. So let's see. So you got negative 11 times 4 is negative 44. Take away 3 times 6 is 18. Negative 62 on top. And let's note it, I'm going to try to make sure that the problems I give you work out pretty nicely. There are a few that work out with fractional results, but I give you those in advance, okay? So negative 4 times 4 is negative 16, minus 15 is negative 31. We get x equals 2. If you go through the same routine for finding the y, x is negative 1. And of course, one of the things you should do is substitute in. I'll just sub in to say the easy one just to give you an idea. 5 times 2 is 10. 4 times negative 1 is negative 4. 10 and negative 4 is 6. The other one checks as well. Okay, so that's how Cramer's rule works in the 2 by 2 case. So what you should probably do is pause the video. Here's one that comes out to be a fraction, and make sure that you feel comfortable. So I'm just going to pause it here, and we'll wait a few moments. Okay, so let's pretend you did this and you came back. Here's your pattern, or tableau, some people say, for Cramer's rule. And again, check to see everything's properly aligned. And matrix D, the coefficients of the x's and y's, 4, negative 7, negative 3, 2, they are on the bottom, okay? And on the top, to get x value, we take the determinant sub x, which means we take the 10, negative 9, and replace the 4, negative 3. And to get the determinant sub y, we replace the coefficients in a y column with 10, negative 9. And here we go, and you work this out. So you get 20 minus 63 is negative 43, and then 8 minus positive 21 is negative 13, and you get this crazy fraction. Okay, you do the one for the y, you get another crazy fraction. That's the way it goes. You get these crazy fractions sometimes. Okay. Before we go on to the 3 by 3s, there is a curious type of problem I'd like to do with you. Okay? And the curious type of problem is right here at the bottom. Okay, so let me see if I can pull that up. We'll look at a better way of looking at that if my eyes don't betray me. Okay, so we're looking at number 2. Okay, now this is going backwards, and going backwards, well, I mean, you have a forward gear in your car, sometimes several, and it's good to have reverse. You can get out of trouble as well. Here's what's happening. I am giving you d and d sub x, and I'm asking for what system of equations got you there. Okay, so this is backwards. That's all right. So don't forget that d stands for the coefficients, okay, of the x and y. So 1x and 2y, 3x and 4y, so that gives you that. And since this is d sub x, that's the determinant where the coefficients of the x have been replaced by the constants on the outside. So that's the 1 and 0. So therefore this setup came from this system of equations. So it's just good to see if you can understand how we go from one setup to the next. Okay. With that said, let's go on to the 3 by 3 case. The 3 by 3 case works the same way. Okay, exactly the same, except the determinants that you're working with are big and nasty. In this case, they're 3 by 3s. Okay, so here's our set of 3 by 3 equations, known as a system of equations. And as usual, capital D is represented by the coefficients in front of the x, y, and z. Okay, and just like before, the d sub x, so if you're looking for x, it's d, this the determinant symbolized by d sub x over the determinant of the coefficients. For y, same pattern. For z, the same pattern. Same thing you need to be careful about here. Okay, and let us now get the others. So the determinant sub x means in place of the coefficients for the x terms, you replace them by the constants. Okay? And d sub y, or the determinant sub y, means you replace the coefficients in the y of the y terms, again, by the constants. And you can see how this works. And then from this point, we're just going to do an example or two. And again, the process is just be careful, and we'll see how this works out. Okay, so let us look at some of the admonitions or warnings, the summary here. Okay, let's talk about what we know happens to the solutions. You get a unique solution if D is not equal to 0, a unique solution meaning a single point, and these of course must likewise be true. And we don't get a unique solution, we get a line or a plane if this occurs. It's called a dependent system. And an inconsistent system is when you have no points in common. So you can take a look at this and just go through with the geometric diagrams I provided when we first began to solve systems of equations. Okay, so let us try, let's try number 3. Okay, and let's see if I can go back and find the solutions for number 3. They should be here somewhere. Is that them? Okay, so let's look at number 3. Okay, so what we're going to do here is we're simply going to write the, whoops, that was number 4. Case 2, is that the one I want to do? All right, let's try number 4 then. Okay, let's look at number 4. All right, number 4 has some missing terms in it. And this is number 4 from, I think it's the class worksheet. Let's just take a look and make sure it's coming from the right spot. Yeah, this is number 4 from the class worksheet. Okay, so what we're going to do is we're going to look at that and see how that works. Now, one of the things that you want to be careful of is sometimes you can have missing terms. So 3 equations, 3 unknown, we expect an x, y, and a z. So notice here that z is 0, here y is 0, here x is 0. So how does that affect us? Well, on the bottom you want your d, which are the coefficients of your x, y, and z. So you get 1, 3, 0, you get negative 1, 0, 1, and you get 0, 1, negative 2. And that goes throughout each of these. Okay? And then let's get the determinants for sub x, sub y, and sub z. For the one for sub x, we replace the coefficients here, which are 1, 3, 0, with 2, 11, negative 3. And there we go. And to get d sub y, we're solving for y, replace the coefficients here, which are negative 1, 0, 1, with 2, 11, negative 3, so forth and so on. Okay? So I'm not going to go through the actual solving because it can be a little bit messy. And what I would like to do at this point is look at an example which I set up for you on Blackboard. Let's make this a little bit larger. Okay, now I set this up on Blackboard. And I call this Cramer's Rule problem classwork. And what you're going to do is I set this up. It looks like a real mess, but believe it or not, this is to get you to be able to do this a little more carefully. It says solve the following 3x3 system of linear equations using Cramer's rule. Use expansion by minors. So this is going to be a little bit tough. Okay, so let's just take a look at the solutions for the first row. See if I have them there. Okay, we're just looking at the solutions for the first row. Okay, now let's not forget what goes here is D, which is the determinant, which is composed of the coefficients. So 2, 3, 1, 2, 3, 1, 3, negative 2, 4, 3, negative 2, 4, negative 1, 1, 3, negative 1, 1, 3. Okay, and let's just work on this one here, and I'm going to give you time, homework time on your own, to go through and actually work these out. And let's see, the rule is, what I'm doing here, and this can be done in several different ways, I'm expanding along row 1. So this would be row 1 for matrix D. So if I first look at the 2, and I cross out everything in that row and that column, I get negative 2, 1, 4, 3. If I then cross out the 3, everything in that row and column, I get 3, 1, and 1, 3. And if I cross out the negative 1, everything in that row and that column, I get 3, negative 2, 1, 4. And then you recall the way we compute these is, since we're going on the first row, the upper left-hand corner has a sign which is positive, and it alternates. So plus, minus, plus. So you got plus, which I didn't show, minus, plus, and we multiply by the actual number. So 2, 3, negative 1. So this is the expansion by minors tableau or pattern I would use for the bottom determinant. Okay, so let's go ahead and let's work this out. So I get negative 2 times 3 minus 1 times 4. So negative 6 minus 4, that's your negative 10 right here. Over here, 3 times 3 minus 1 times 1. So 9 minus 1 is 8. Okay, over here I get 12 minus a negative 2 is 14. And then of course I've got plus 2 times negative 3 minus 1 times that. So I get negative 20 minus 24 minus 14. That should give you negative 58. Okay, and once you have this set up, this is the determinant where the coefficients for the x, because this is d sub x, right? We're solving for x, are replaced by the constants. So the first column is replaced by negative 9, 16, 2. And again, let's set this up. This is called, again, expansion by minors. I'm going to expand along row 1. So I'm going along row 1. Start with the negative 9. That comes on the outside. And next one I'll be multiplying by a 3. And next one I'll be multiplying by a negative 1. And I go plus, minus, plus. So that becomes a minus. This becomes a plus. We're going to work that out. Now, if I'm working with the upper left-hand corner, I'm blocking out everything in that row, everything in that column. I get negative 1, 2, 4, 3. If I'm then working with the 3, everything is blocked out there and there, so I get 16, 2, 1, 3. And if I'm now working with the negative 1, I block out everything there. I get 16, negative 2, 2, 4. I'm going to work this out. Okay, so let's see. Negative 2 times 3, negative 6 minus 4, negative 10. 16 times 3 is 48, minus 2 is 46. And 64 minus a negative 4, 64 plus 4 is 68. Work this out, negative 116, so x is a 2. Okay, this is on Blackboard. Work it out. I'm not saying it's easy, but you can do it. And we'll come back. We're going to do a second one of these videos, a little more practice. And hopefully you'll be good enough at this to do the take home, which is just like this, really. But you have to go through step by step. Okay? So, talk soon.